and then you shift the position, and you end up with having velocity difference times mass times an average velocity. At this point, with a very rough mathematical trickery, multiply by 1, numerator is a variable, denominator is a constant, then take derivative using variable at numerator, we say this thing. 1 meters over meters, 1 the delta x, I put the delta x inside the square brackets, and the x I leave out the x outside the square brackets, and then when taking the derivative, we derive in respect of that x, and we obtain this formula for the damping force with the coefficient, the damping coefficient and the velocity. I came up with the idea yesterday that maybe it's even smoother if we consider that in the formula of the kinetic energy at the bottom of the page of the slide, we can, for example, take the average velocity and consider there is meters on seconds. So we can put the seconds inside the square bracket, and we leave the x outside, the distance outside the square bracket, and we can derive. And once again, we have mass over kilograms on second times delta V. But somehow this is a trickery somehow. Okay, the terms in the square brackets as once again kilogram over seconds as dimension. Now onto the interpretation of this term, that would be the damping coefficient, that is to say how much the term or subsystem, damping subsystem, can slow down motion of the system, the poor oscillator. So in my mind I think something like this. The greater the mass I can stop, given same velocity variation and space to stop it, the greater I'm damping. Think at a truck versus a bike that stop in 10 meters from 50 kilometers an hour. So the greater the variation in velocity at numerator, given same space and mass, the greater the damping. The lower the space in which I obtain this velocity variation, the greater the damping once again. Back in the day, I made some simulations in MATLAB, and results were quite good for an underdamped system, but not that good on for an overdamped system. 10% error on initial velocity condition, and better on displacement initial condition. Error in respect of the logarithmic decrement method. Results were better when averaging with same formula but lifted on one temporal order, that is to say mass times delta acceleration on delta velocity. Averaging that number with the one given by mass times delta V on delta X was quite close to the numbers given by the logarithmic decrement method. And still the interpretation of the mass of that mass remains quite unclear. For example, if you think at two rubber dampers with same ratio delta V on delta X, and same oscillating systems acting on them, maybe the mass could be the damper mass, so that the bigger one, volume, or the denser density, one dampens more than the other one. And about elastic dampers, like rubbers, I tried to translate the formula, including more material-specific information, and the trial formula obtained purely playing on the dimensions, so that is not verified at all. The formula I arrived to was this one, where ρ is the density of damping material, E is Young modulus, E dist is distortion energy while compressed under load, S are seconds as usual, so that the material dampens more and more as it's dense, ρ at numerator, is soft, that is to say small Young modulus at denominator, and as it's absorb energy, distortion energy, big distortion energy, and doing it fastly, little small seconds, that is to say somehow the velocity of distortion. Velocity, so power of distortion power. Another model of damping coefficient came into my mind when I took the inspiration when I took inspiration from electrotechnics because of the similarity of force equal CB, that is equal to volts equal resistance times current. So resistance, we know that has these two formulas. And resistance has ohm as physical dimension. There are watt over ampere squared, ρ, maybe in English resistivity. Dimensions are ohm times meters, and then L over S, length over area, somehow cross section area, are the inverse of distance, 1 over meters, 1 on meter. So the physical dimension of damping coefficient and resistance are the same. And just to recall, ampere has a physical dimension coulomb over seconds, or charge per second. So if we switch charges for distance, we have that amperes are meters per second, that is to say velocity. So C can have this expression, force squared over watt power, or else C is watt power over velocity squared. If we put together these relationships, the one for resistance, the physical dimension, the resistivity, 1 over meter, and C as power over velocity squared, we might say that C is equal to, with respect of the formula of resistance, equal resistivity length over section, cross section. That C is equal to C0, 1 over meters. That is to say, watt over velocity squared times meters times 1 over meter. As for the C0 term, we can develop in this way, and we end up once again with this mass times delta V, or mass times velocity, so that C is equal to C0, 1 over meters, or 1 on meters, which is mass times delta V times 1 over delta X, which is once again this formula. What is delta X is at the moment unknown. Alternatively, we can leave we can take this formula, and then we can leave power, so that we end up with power over acceleration. That is quite interesting, or force times velocity on acceleration, or over acceleration divided by acceleration. This last formula can be quite interesting, because if we are modeling the coefficient, we have force, we can give force to the system, then we read on the accelerometer the acceleration, and integrating it, we obtain velocity. Maybe if it's velocity, maybe it's delta velocity, the variation. However, there's still the inverse of the distance to interpret. S could be the frontal area of the mass, V the volume, but while it's easy to imagine that a big area offers more resistance than a small one, it's more difficult to visualize a small volume that dampens more than a big one. Or once again, we can leave the distance as a denominator and say C equals C0 times 1 over meter, and we end up with this formula that in the end is always the same. Once again, we give force, the less the acceleration we read on the accelerometer and the greater the negative jump in velocity between cycles, and the smaller the distance or displacement in which this slowing down takes place, the greater the damping subsystem power is. But we have to further investigate on the nature of these quantities because all of this is purely abstraction, hypothesis, and ideas. Whatever formula we use, however, there's always a quadratic exponent of the velocity. Once we multiply damping coefficient per velocity itself, thus exiting linearity. So final recap, alright, so let's recall the formulas we have seen so far. The equation of motion with the inverse Fourier transform of zeta. Zeta is this one formula. In case the pure oscillator, there's no damping coefficient. So the inverse Fourier transform becomes this formula relationship in time domain, and hence the final equation of motion in time domain is this one for the pure oscillator without damping the real part, the damping coefficient. If real part of damping is present instead and it's frequency independent, we have this relationship, this formula. In the case of frequency dependent real part, I try to imagine all of these relationship that you can see. And we are done. Feel free to comment or contact me, and because we are on YouTube, subscribe please and click on the notification bell to receive updates on this and other ideas that I come with. And consider to give a thumb up too, and share link out of this video with anyone that could be interested in this topic. So until next time, our video slide, stay strong.